Hello, today we'll be introducing game theory, more specifically the Minimax Theorem. Our speakers today will be Charles, Bang, Maria, and Iris.
So first, some background information on game theory. Game theory involves rational decision makers making decisions and moves based on what the other players in the given situation or game are doing. This means that the choices are interdependent and influenced by something external that the player has no control over. Game theory helps to determine the most probable outcome of the given situation. Some common examples of game theory problems are the prisoner's dilemma, seen in the chart below, and the dictator's game. There are many applications of game theory outside mathematics, but within game theory, predictions can be made throughout matrix calculations. Minimax is a concept that involves trying to reduce the worst-case potential loss. With this, during a game, someone would consider all their opponent's possible choices and outcomes and use their options to reduce the loss from their opponent's potential best choice.
Next, we'll talk about how the Minimax Theorem was derived. The Minimax Theorem was first proven and published by John von Neumann in 1928. His theorem states the following. Let x and y be compact convex sets. If the function is a continuous topologic function, which is a continuous convex concave function, then if 1, for any fixed x-coordinate, the function is a continuous convex function of y, and 2, for any fixed y-coordinate, the function is a continuous concave function of x, then the Minimax theorem is true, shown below. This means that there is at least one saddle point in the function. I've also included a very brief proof with the relevant theorems. Essentially what this proof is saying is that in a zero-sums game, the amount that player 1 gains is equivalent to the amount that player 2 loses, and vice versa. I've also included a link for a more elaborate proof.
Okay, I will be talking about two-person zero-sum game. So in a two-person zero-sum game, there are two players, and each of the players is given various choices between a bunch of moves, and each player loss is equal to the other's gain. So there is a payoff matrix that describes the state of game between two players, and the ij entry of the matrix is the payoff that accrues to the role player when the role player makes the move I and the column player makes the move J. In this example here, we can see a very simple payoff matrix. We can also call this a game matrix for simplicity. And it is since this is a pretty simple matrix of a pretty simple game, most of us already know about this game. So rock bits scissors, scissor bits paper, and paper bits rocks. So each +1 entry indicates that there is a win for role player, a -1 indicates a loss, and 0 is a tie. So what the role player wants to do is to net in the largest points possible. To do so, the role player can play it several different ways. If they don't know about game theory yet, they could play it the naive way by either go with the pure strategy where you just go with one option for every round. The other would be going randomly at each choices. And when I say randomly, I don't mean like completely, absolutely random, but more like there's a distribution for each move that the player would play at each round. So when we play a game using the naive approaches, we can calculate the expected value that the role player is going to gain from that game. And the formula is the expected value equal to role player probability matrix times the payoff matrix times the columns layer probability matrix. Consider an example. Here we have the payoff matrix P that describes the current state of the game. We have the probability matrix of role player. We can see that they would play the first move 75% of the time and would play the third move 25% of the time. This person do not play second move ever, and we can see the column player preference as well. they would prefer to half of the time go with the second move and half of the time go with the third move. So we know the payoff matrix, we know the row and columns player probability matrix, we can calculate the expected value that row player is going to gain from this state of the game, and that value is negative 0.125, which means that the row player would be at a disadvantage with these probability matrices. Now, if the role player have knowledge about game theory, they can use the Minimax algorithm to gain some more advantages. A player using the Minimax algorithm chooses a strategy that, among all possible strategies, minimize the effect of other players' best counter strategy. In another word, choose the optimal strategy that can minimize the maximum damage that the opponent can cause. When analyzing a game, we always assume that each player makes the best possible move, and each player knows that his or her opponent is also making the best possible move. Finding the minimax strategy is called solving the game, and one can simply solve the game by, or at least simplify it by the reducing by dominance technique or the settle point technique.
Working with matrices in game theory. So in game theory, the game matrices detail the playoff of the game between each player. The player 1 represents the rows, and player 2 represents the columns, and each entry in the matrix represents the playoff given what move each player makes. So here we have, if player 1 makes the first move that they can make, so that first row, and player 2 makes the first column move, we'll have a playoff of -2 for the row player or player 1. In the same way, if we get the row player doing their second possible move in that second row, and the column player doing the third move that they can make, we'll get a playoff of -3 for the row player. So that's how these game matrices can be analyzed and used to understand what the playoff for each player is in the game. So reduction by dominance is a good way to figure out what the best playoff for a given player is. So to make the matrices easier to work with and to determine the best options and payoffs for each of the players, they can be reduced by dominance. And these are the two rules for eliminating rows or columns. A row can be deleted if there exists a row with that will produce a payoff of equal or better value. And similarly, a column can be deleted if there's another column that will produce a payoff of an equal or better value for the column player. That's kind of difficult to understand, so I have examples here. So here's an example. We have this game matrix for the row player, where the rows represent the payoffs for player 1, and the columns represent the payoffs for player 2. My bad. So for this one, you'll see that to eliminate it, we have higher numbers in the columns represent a higher payoff for the column player, in the same way that the higher numbers in the rows represent higher payoffs for the player 1. So if we look at this based on the two rules we had before, we have this very, very last column 3, where all of the values in that column have much higher payoffs for the column player than they do for the row player, given that if the row player makes any of those moves and the column player just makes that one move, that the column player will always come out with a higher payoff. So we can eliminate that column, and shown here at the bottom is the matrix after we reduce it by dominance. And going back to our initial example to show what this would be like reduced by dominance, we have first we can reduce it in terms of rows by getting rid of that very middle row, since every entry in that row is less than every entry in the very third row. So then we'd be working with those the very first row and the third row only. And we can also get rid of the second column, given that those values are very high for the column player, and we want higher values for the row player. And that pretty much concludes the reduction by dominance bit. Thank you.
Now that we have studied reduction by dominance that apply to a real matrix, consider the following game matrix is a payoff matrix. row player can choose move 1, 2, or 3, and column player can choose move A, B, or C. We are playing as the column player, so let's try to reduce this matrix. The first step, we notice that row 2 dominates row 1. This is because every element in row 2 are larger than those in row 1, so we can get rid of row 1. Step 2, we notice that column B dominates column A and C, so we can get rid of column A and C. Column B dominates column A and C because its elements are less than those from column A and C. It's reversed from row. This is because when we look at column, we are looking at the point of view of the column player, so everything is reversed with the row. So instead of finding the row that has the largest elements, we are finding the column with the lowest elements, and that is column B. Now move on to step 3. It's pretty simple. We see that row 2 dominates row 3. This is because 0 is larger than -2, and so we get rid of row 3. We are left with only one cell, that is 2B. So choosing the move 2 is the best option for row player here, and consequentially the best option for the column player is to choose move B. Now we move on to another technique, that is the saddle point. A saddle point is the payoff that is simultaneously a row minimum and a column maximum. To locate a saddle point, we find a row minimum, and then we box in the column maximum. So again, it's strictly determined if there is at least one saddle point exists in its payoff matrix. The following statement are true about strictly determined games. First thing is that all saddle points in a game has the same payoff value, and also choosing rows and columns through any saddle point gives the minimax strategy for both players. In other words, the game is solved via the use of pure strategy. The value of a strictly determined game is the value of the saddle point entry. A fair game has the value of 0, and if it doesn't have the value of 0, then the game is unfair or is biased. The application for saddle points is pretty simple, really. Consider the previous example. This is the payoff matrix that we used for our example before. We can see that there are 2 saddle points highlighted in this matrix. They are both 0. You can notice that they are the minima of their row as well as the maxima of their respective columns. Both of them are equal. This is true with what we have stated before. And since they are 0, we know this is a fair game. Finally, let's talk about the real-life application for game theory. Game theory is essentially the study about the human behavior and decision, if you make it simple. So it can predict a lot of things. It can predict the voters' preference. It can predict the behavior of your consumer. It can help you in sale negotiation or pricing decision. This can also help you in real estate transaction. I have put a link down here if anyone wants to read more about this stuff, but since this is not the core message of this presentation, I'm not going to go deeper into this. And this is the end of our presentation. Thank you for listening, and this is a quote from Vinet Kapoor. A game is constructed to secure unrestricted freedom within a highly restricted setup.